All right, everyone, our next session is building PCI-compliant Kubernetes platforms, demystified, fun, and possible. Handing it over to Julien and Tarun from Akamai.
Thank you. Hey, everyone. Welcome, and thanks for joining us. Today, we'll talk about how we're building and you can build a PCI-compliant platform that is based off Kubernetes. We'll try to demystify a lot of it, show how it was possible, and how it was fun. And fun to set expectations is fun, more fun in cloud native than it is traditionally without cloud native. I'm Julien. I'm a senior architect for the Akamai Cloud. I work on cloud-native products, including our publicly managed Kubernetes service, as well as our internal platform that is also based off Kubernetes. I'm also a technical lead within the technical advisory group within the CNCF for the developer experience.
Hi, I'm Tarun. I'm a principal software engineer working on the cloud-native team within Akamai.
All right, looking at our agenda for today, we'll go from why PCI on Kubernetes is traditionally tricky, and then we'll deep dive into some of our architecture, and then concrete examples on what we've done to solve this within our platform. So first, we have to look at why PCI on Kubernetes is tricky, and to better understand it, we have to first look at the cultural clash. So with PCI, traditionally, we have strict controls, we have audits, and we have very manual evidence trails. Then when you compare this to Kubernetes, we have highly dynamic environments, we have multi-tenancy, and we have fast-moving environments. Looking more closely at the traditional compliance checklist, we have manual evidence collection, we have periodic audits. Then comparing this to the cloud-native philosophy, we have continuous automated changes and declarative configuration. Taking another example, with the PCI and traditional compliance checklist, which traditionally have static infrastructure with static access control rules, and then comparing it to cloud native, we have ephemeral infrastructure, both for pods, but also for nodes that can dynamically scale up and down. So combining all of that gives us an environment where we have to balance the compliance requirements with the agility that Kubernetes traditionally gives us. We have an extra challenge in our case. We don't have any managed Kubernetes that is PCI compliant within the Akamai Cloud yet, so we had to build our own. And the good news here is that it is possible and it is fun, as long as you stay close to the cloud-native philosophy, as well as embracing automation and making smart trade-offs. So we have three major guiding principles here for our platform. The first one is GitOps, we have Zero Trust, and we have shifting compliance left. Taking a closer look at GitOps, we have approval for changes. GitOps first is using Git for infrastructure and application definition within Git, and not just using it for code. So what that gives us is it gives us approval for changes, gives us immutability of the desired state, and auditability of all the changes, and a way to do changes in a unified fashion centered completely around Git. Here, we don't reinvent the wheel. We just use the same tried and tested patterns that we have for code, and we apply them for infrastructure. Looking at Zero Trust, here we try to reduce the risk of accidents happening, as well as lateral movement in case there's an eventual compromise. So everybody basically gets the least powerful amount of access, and then we combine this hand in hand with the GitOps processes that we have to have a clear process for escalating privileges. What that gives us is it gives us that process for escalating privileges that is documented and approved exactly like we do for our code. We feel like the success here of Zero Trust is making it easy and on by default within the platform, so that to be able to empower that, we have a way to enable a single sign-on with nearly zero configuration, as well as role-based access control. We'll talk about that in the future slides. And then combining all of this, as well as adding compliance in the continuous integration stages, is what allows us to shift compliance left. We build processes and our platform with compliance in mind, and we don't leave it as an afterthought. Now I'll pass it off to Tarun.
Right. So looking at the high-level architecture, users interact with the platform's control plane via a central management cluster. The management cluster is globally managed. It is managed by the platform's SRE team. The SRE team is responsible for making sure it has backups, it is resilient, it's fault tolerant, all of that good stuff. We drink our own champagne here. The management cluster is an instance of the platform itself. The management cluster uses Crossplane in conjunction with ArgoCD to create what we call application clusters. We use Ansible to deploy RKE2 on those VMs. We chose Crossplane and Ansible over Cluster API due to Cluster API being relatively new. When we started this, we wanted something more mature at that time. We are now moving towards a model where we use Cluster API. Now, diving a little bit deeper into the application clusters, what are application clusters? Each user or a service gets their own cluster, basically. Application clusters are an instance of the platform. They are Kubernetes supercharged. We chose RKE2 as our Kubernetes distribution because it has an easy path towards compliance, like it has built-in supports for CIS profiles, it's easy to configure, it has hardened images, all of that good stuff. We also install a number of components such as OpenTelemetry, Cert Manager, Trivy, and also default configurations in line with our organization's policies. So teams can just get the platform off the shelf, put their app on it, and they are already on the path towards compliance. The platform is also versioned as a single unit. So teams don't have to worry about what Kubernetes version am I running on, what version of Trivy do I use. They just worry about what version of the platform they use. Application owners, however, still have to make sure that their use of the platform is compliant. The app clusters also come with SSO enable for kubeconfigs, just like Julien was talking about earlier. Any usage of higher level credentials is automatically monitored, and we have alerts written for it. We'll dig a little bit deeper into that in the next slides. All right, tying our architecture back to our original principles that we are talking about. When we say we use GitOps for everything. Literally everything is in Git. We put our topology and configuration of our clusters in Git, everything from alerts to dashboards to all your application manifests are in Git. This lets us use tried and tested patterns like branch protections, code owners, and all of that stuff to just reuse everything that you've built for your applications, but use it for infrastructure. We also managed to find a way to make our OS versions sort of declarative using the Ubuntu snapshot service. Ubuntu has a pretty neat service that lets you choose what date you want your packages to be available from. Like, it just gives you versions of those packages that were latest at a given date, so you can pin without going too deep into the details. The other thing that this gives us is a common deployment framework for all teams. Teams can deploy their apps using internal best practices. This lets SREs within the organization cross-pollinate ideas, build common tooling, and generally upskill themselves without having to repeat or identify new patterns. We use ArgoCD and Crossplane. GitOps and ArgoCD acts as a single pane for change, approval, and evidence. PCI is all about evidence gathering and approval and documentation and all of that stuff. This makes the path towards it super easy. Crossplane also helps us extend that to infrastructure too. So any manual modification that anyone does to the state of their cluster is instantly reconciled and put back. Crossplane also has management policies that help us prevent accidental deletion of resources as well. Okay, looking at the security controls that come as part of the platform, the management cluster or the platform itself is deployed via GitHub Actions. GitHub Actions allows us to easily solicit and record approvals from multiple stakeholders, again, which is a PCI requirement. This also helps us maintain an immutable log of events, who approved it, when was it deployed, all of that stuff is all automatically tracked. We use Trivy and OS query to do continuous vulnerability monitoring. We install Trivy on the application clusters and on the management clusters to continuously scan all OCI packages on the cluster to know if there's anything vulnerable running. We also automatically enroll all cluster nodes using OS query into our fleet management tool, Fleet DM. This lets us quickly find out if a vulnerability breaks out. For example, last week's runC vulnerability, we didn't have to scramble to figure out where the vulnerable version was running. We already knew, and we just had to bump a version in our manifest to get the fix. We use Cilium along with Hubble and Istio. Cilium is a great CNI. Everybody loves Cilium. Cilium has great network policies that let us tighten access control within the cluster. We use Istio and Cilium together because Istio is used for pod-to-pod encryption and also as a service mesh. We don't have native transparent encryption in the network, so we use Istio's capabilities for it. We use Hubble to figure out what traffic was going inside the clusters. You can't block or you can't you can't restrict what you don't know is happening. So we use Hubble to surface that level of observability, and then built our policies using that. Audit logging, all actions are logged. The Cube API has a neat API to enable audit logging, has filters by default, so we enable all of that stuff. We also log the credential usage. Like I mentioned earlier, we have some admin credentials. We'll dig a little bit deeper into this in the upcoming slides, but we log all of that. We send it to Loki, and then we also externalize some of the data to Security Onion, because Loki has some challenges meeting PCI requirements of keeping data for 90 days hot and 1 year cold. We use RKE2, and RKE2 has an easy way to use to enforce CIS policies. We use Kyverno on top of it to further fine-tune those policies. Now we are going to dig into that a little bit deeper. Now, this is an example of an admission configuration. This is a basic Kubernetes feature that is offered. RKE2 just enables this when you enable a CIS profile. So it enforces the restricted policy on all pods in the cluster. And take a look at the exemptions field. The exemptions only lets you do username exemption, runtime class, or namespaces. Now these exemptions are too broad. You don't want to exempt an entire namespace from following the pod security policy rules of least privileges just because you couldn't get one third-party component to run as non-root. So what is the solution? Enter Kyverno. So in the example that I'm going to show you, we have a rule that lets STO run as non-root. In the ingress namespace, to do that, we used a Kyverno cluster policy that enforces the pod security policy for all pods in the cluster. But we also have a policy exception that says, in the ingress namespace, just let the STO container run as non-root. So this is a layer of control above and beyond what pod security policies by default can do. So this is how we have, by following the principle of least privilege, reducing privileges of what can run inside the cluster. Looking next at the logging monitoring, this is an example snippet from the Loki config map. This is an alert based on the log events. We're using Loki to monitor and enforce credentials used to create and instrument application clusters are only used from the sources that they're intended to. If you think back to our architecture, we use Ansible to deploy RKE2 on these nodes. Ansible logs in as root. So it needs root access. So we can't say, don't use root. So we use root access, but we have to make sure that we only use root from a known set of IPs and a known set of actors. In this case, the IPs you see here are the IPs of the global management cluster. So this IP list is dynamically kept up to date. So whenever the management cluster scales, or we add a new node or remove a new node or remove an old node, this IP list is automatically kept up to date. So anyone else logging in as root will get an alert. Same for kubectl emergency credentials use. The alert name is weird, but this is meant to catch anyone other than ArgoCD using these super admin credentials to apply things onto the cluster itself. So we want our users to use least privilege, like we've been saying again and again, use least privilege. So if they use the super admin credentials, any actor other than ArgoCD, we catch it. It's a source for investigation. So the key takeaways is that this setup guarantees high privilege credentials are never used outside of controlled automation. It strengthens our overall platform integrity and compliance posture. It also makes sure that we always investigate any possible suspected misuse. The other thing that gives us is the declarative manifests serve as exception documentation for the audit. So during audit time, we don't have to scramble to figure out what rules we are following and what rules we are kind of working around. So this manifest can serve as documentation for that as well. Over to you, Julien.
Thanks, Tarun. So looking at one of the critical requirements of PCI is the identity of and access of all the administrative users that are logging into the application cluster. So SSO single sign-on here is core. It allows us to map all the actions that are happening on the application clusters to the individual users doing them. So whether they're using kubectl or any other tool that interfaces with the Kubernetes API, all the actions are authorized for these individuals and logged under their name. Making those kind of things easy to do in the platform is what empowers users to have an easy path for their PCI as well. To be able to power all of that, we use the built-in OIDC capabilities from the Kubernetes API. And then we combine this for kube login to handle the OIDC callbacks that are happening on the local host, so the computers of the administrators. And then we combine this with OIDC PKCE for the authorization flow. That's basically a way to use only public keys to do the authorization for OIDC. So by combining all of this, we're able to have absolutely no secret in any of the configuration for the single sign-on. That means neither the servers or the clients have any secretive information. That means we can push the same configuration for OIDC to all of our users. That means that they can onboard OIDC, RBAC, and SSO in a very frictionless way because they don't have to engage with the identity team to enable their clusters. Everything can be done out of the box within the platform. So if we take a look here at our example, I just want to point out first, this is something that our platform offers here. We have a simpler configuration format that basically encompasses how we configure the platform, so our users don't necessarily have to use the Kubernetes manifests. Hiding the complexity of Kubernetes is something that allows the more novice cloud-native users that are within Akamai to be able to approach the platform. It also makes it less verbose and potentially easier to review during the pull request review process because these configurations tend to be less verbose here. Deep diving into our example, here we see that we have the product developer groups that is being assigned a role that is built into the platform. So our platform users don't have to do anything to have access to these roles. They just are out of the box within the configuration, so they have access to a read role. Product SREs have access to a role that is more powerful that provides them with read-write. And then in the case that we have here, the platform user in particular wants to define their own cluster role that is able to read nodes and pods that they want to provide level 2 support with a very basic level of troubleshooting. They can still define their own role with a traditional Kubernetes resource and then start assigning it in the simpler configuration format. So using all of these patterns here allows us to assign permissions via GitOps. It allows us to leverage the exact same processes for permissions than we do for code. That means we can use code owners to control who can approve these kinds of requests. We can use branch protection to prevent accidental or non-accidental modification of these files. And we can use CI checks, so continuous integration checks, to be able to validate the sanity of these files and the permission changes. So then once the change is approved and merged, this is going to be rendering the actual cluster role binding. So the simpler format is being expanded into the actual cluster role binding here. The key aspect of our platform here is that they can use the simple configuration format, but they can still have access to any Kubernetes resource. So that means that the users that are power users with complex use cases can still use all of the power of Kubernetes, but then the novice users are able to approach our platform with that simpler configuration format. That makes it less daunting to approach our platform as well. And then today, the way you enable OIDC and single sign-on is through this simple Boolean and then starting to map the roles. What we want to do in the future is to have zero configuration for OIDC and single sign-on, so it has to be enabled by default across all the environments. So that includes development, pre-production, production, any environment will have this enabled. And then what we can do with that is we can do things like, for example, the development application cluster of our users can provide full access, for example, or very broad access by default to all the owners of the application clusters, and that can all be done by default, while production has a very strict control by default, still with SSO enabled. And then having these kind of things enabled by default in our platform makes it much easier to onboard for the users. It makes the action audited, so any action that happens, whether it's in any environment, all gets audited, and it also creates an offboarding story that is much easier because all the clusters, even the dev ones, are SSO enabled, so offboarding a user is extremely simple here. Next, I want to talk about one of the core principle and decision of our platform here, and it's our shared responsibility model. So as Tarun mentioned in the architecture, each user gets one or many app clusters that are all managed by a common platform control plane. We have to look at the goal here of our platform team. Our goal here is to empower our users to build PCI compliant systems, and it's not to build PCI compliant systems for them. So what that means for our responsibilities as a platform team, we create a PCI compliant control plane that is able to provision and manage the lifecycle of PCI compliant systems that are under the control and management of our users. We also ensure that teams have access to common tools as well as a golden path for their PCI compliance. And then looking at their responsibilities, they have to leverage the platform to build their own PCI compliant systems. And then along the way, they have to ensure their usage and the way they develop their software, whether it's the code or the manifest for their infrastructure, they have to ensure that it complies with PCI, because in the end, their compliance is their responsibility. They also have to handle any cardholder data requirements. We don't handle these in the platform today because the platform control plane does not need to handle these. They can use the common tools and processes that we have to create their own story there, but in the future, we want to potentially enable them to do that in a more native way within the platform. Combining all of this gives us an environment where each platform user is able to own their own compliance story, but where answers can be reused across systems. And we have a lot of common tools as well as processes to allow users to achieve their compliance goal. So here we want to close on a thought that we think represents how we tackled the journey to PCI in cloud native, and it's be better than them, be better than they. Which to us means it's not because PCI traditionally equals heavy processes and static infrastructure that we can't make it work using cloud-native principles. It's also not enough to match the old models when doing compliance. We can all do better as we build our cloud-native platforms. And with that, thank you very much, and we'll take questions.
I'm curious about your management control plane cluster and how your team is managing changes to it. Like, we have very similar, but I'm in healthcare, and we have a Argo control plane, and we have like two environments, basically dev and production. And so, we deploy one breaking change in dev, we think we fixed it. Production's a lot scarier. So I'm just curious how you guys are managing that.
Yeah, we do something that is pretty similar to what you do, where we have even more layers than that. We have an environment where our QA teams are actually qualifying changes. Then we have a staging environment where we put actual real releases and get them requalified. Then we push them to a lab environment that all of our users are using like it is production for their application clusters, but it's not their production. It's their own pre-production, and then once it's done, we then escalate that, and it's the real production. So we have a lot of phases to be able to push these changes, and they're all controlled through a GitOps-based SDLC that we use ourselves to be able to promote.
Okay, so you have like the developer, you have a control plane for a lower level environment for developers as
Yes.
also as yours. Okay, interesting. Thank you.
Any other questions? One over here.
Thank you. As far as I understand, so you mentioned that you're using management cluster to create application clusters. I wonder, how do you manage version upgrades for the application clusters, and do you allow application teams to configure a set of additional services for their cluster? And yeah, that's the question.
Can you just clarify just the last part? I didn't hear.
So yeah, so you're using Crossplane, as I understand, cluster resource to create application clusters. So if you have many clusters, I assume they can run on different versions, and different application teams may want different services running with them. So how do you manage upgrades of Kubernetes versions on those clusters? because applications can have dependencies on the version of the cluster.
Yeah.
So this needs to be coordinated, and also how do you upgrade the services as well?
Yeah, basically what we do is we bundle the whole application cluster platform as one single unit. So for example, in the platform version 1.0, it will come with a specific Kubernetes version, as well as a specific version of all the components that we're shipping within the cluster. So all of these are tied to a specific platform release. Then let's say we're upgrading Kubernetes, then we may or may not decide to upgrade the version of the platform components, but these are all set together, and when our QA team is qualifying these, they're qualifying that whole bundle of version, the Kubernetes version, as well as all the other versions. We don't allow mix and matching the versions of the components. So for example, Grafana and Loki have to be on a specific version for a platform version, and everything is bundled together as one whole unit and upgraded as one whole unit, which allows to test, like the version matrix is much smaller because there's much less paths to test here.
Yeah. And the other thing to note is the application teams choose when to take a new version of the platform. So we make the newer versions of platform available in the testing environment. Application teams test their changes, their compatibility of their application with the newer version of the platform in the test environment, and then they promote it to production once they feel ready. So the platform team's job is to put out new versions of the platform, make sure it's stable for a sample use case, for a targeted use case, and the application teams choose when to upgrade. They may have different priorities. So.
All right, we'll try to do one more question.
Hey, great presentation. I'm curious how you're handling vulnerability management when it comes to kind of trying to get those upgrades and vulnerability patches out as quickly as possible with a bundled platform version like that.
Yeah, that's a challenging piece indeed, because for example, we may support multiple platform versions, especially in our environment. We have users that don't necessarily have a tendency to upgrade at a fast pace because their system is complex, and taking Kubernetes upgrades is not necessarily simple. So basically what we do is we publish a supportability window that we have for all our releases. So for example, we'll support versions as long as they're supported by Kubernetes, is basically what we say. So platform versions have about a 1-year window of supportability from our team. So that allows us to have a more limited amount of versions to support. And we also, when there are any vulnerabilities, since we have a central platform control plane, we know exactly who is running which versions. So we know what versions to prioritize when we're getting these kind of vulnerability fixes out of the door. We can know which versions to prioritize because we know which versions are being used both in lab environments and in production environments. So depending on the complexity of how to fix the vulnerability, we may decide to prioritize only the clusters that are in production, for example. That's something that we can do. We haven't had to deal with an event where we had to not push all the supported version. That's something that we would be able to do through our global pane of glass that lets us know which versions are in use.
All right, I think we have to call the questions there. Julien, Tarun, thank you so much.
Thank you.